Have you ever considered how one molecule with the exact same formula can have a completely different structure and therefore different properties? Welcome to the fascinating world of isomerism. Isomerism is a peculiar phenomenon in the realm of chemistry, where we see that two or more compounds, despite having the same molecular formula, can have entirely different structures or spatial arrangements. This, in turn, leads to these compounds having different properties. It's kind of like having identical twins with completely different personalities. Imagine the possibilities. Isomers could have different colors, different reactivity, or even different states at room temperature. So one can understand that it's not just about what atoms a molecule has, it's about how those atoms are arranged. The study of isomerism is a cornerstone in the field of chemistry, crucial for understanding the behavior and properties of molecules. Now, imagine two objects that are mirror images of each other. Can you superimpose them perfectly? In most cases, you can't. This is the principle behind enantiomerism. When we talk about enantiomerism, we're delving into the fascinating world of stereochemistry. It's all about how molecules occupy space and how they relate to each other. Enantiomers are a pair of molecules that are mirror images of each other, just like your left and right hands. Hold your hands up, palms facing each other. They're mirror images, right? But try to lay one hand on top of the other. You'll find that they just don't match up. This inability to superimpose is a hallmark of enantiomers. But you might ask, what sets enantiomers apart from other isomers? Well, it's their unique relationship with plane polarized light. Enantiomers have the ability to rotate plane polarized light in equal amounts, but in opposite directions. This optical activity is a unique characteristic of enantiomers, and it's a fascinating aspect of stereochemistry. Now, let's contrast enantiomerism with diastereomerism. Diastereomers are also stereoisomers, but they're not mirror images of each other. And like enantiomers, they're not superimposable. However, unlike enantiomers, diastereomers do not always exhibit optical activity. Think of diastereomers as siblings from the same family. They share some features, but are not identical. Just as siblings can have different hair or eye color, diastereomers can have different physical and chemical properties, such as boiling points, melting points, and reactivity. With enantiomerism and diastereomerism, we see that even small differences in how atoms are arranged can have a significant impact on a molecule's properties. It's like a molecular game of spot the difference, where the differences can have profound implications for how these molecules behave and interact with the world around them. Enantiomerism and diastereomerism are key aspects of stereochemistry, which explores how molecules occupy space. This understanding forms the basis for much of organic chemistry, and as we delve deeper into this topic, you'll see just how fascinating it can be. In the mirror world of molecules, left and right take on a deeper meaning. They are the R and S configurations. We're venturing into the realm of stereochemistry, where molecules can be mirror images of each other, much like our left and right hands. Let's start with the R and S configurations. These labels come from the Latin words rectus and sinister, meaning right and left respectively. They are used to describe the three-dimensional arrangement of atoms around a chirality center, often a carbon atom with 4 different groups attached. The process of assigning these configurations involves several steps. First, we identify the chirality center and assign a priority to each group attached to it based on atomic number. The group with the highest atomic number gets the highest priority, and so on. Next, we orient the molecule so that the group with the lowest priority is pointing away from us. From this perspective, if the remaining groups decrease in priority in a clockwise direction, the configuration is R. If they decrease in an anti-clockwise direction, it's an S configuration. Now, let's turn our attention to meso-compounds. These are special types of molecules that contain multiple chiral centers but are overall achiral, meaning they do not rotate plane polarized light. This is because they possess an internal plane of symmetry, causing the mirror image of the molecule to be superimposable on the original. In simpler terms, think of meso-compounds as a pair of gloves. Each glove, or chiral center, is unique, but when you put them together, you get a symmetrical pair that is indistinguishable from its mirror image. These concepts might seem abstract, but they are critical in understanding how molecules interact with each other and with light, influencing everything from the taste of our food to the effectiveness of our medicines. Understanding the R&S configurations is like learning a new language, one that allows us to describe the three-dimensional world of molecules. Geometric isomerism is like a molecular dance, where the partners can change positions but remain connected. Picture two dancers holding hands, spinning around a central point. This is the essence of geometric isomerism. In the world of chemistry, these dancers are atoms or groups of atoms, and the central point is a double bond or a ring structure. The dance is the spatial arrangement of these atoms or groups, creating different isomers or versions of the same molecule. Let's delve into the two main types of geometric isomerism: cis-trans isomerism and easy isomerism. These terms may sound complicated, but they are simply ways to describe the different positions the dancers can take. Cis-trans isomerism occurs when two identical atoms or groups are on the same side, cis, or opposite sides, trans, of a double bond or a ring. Consider two dancers spinning around but always staying on the same side of each other. That's cis-isomerism. On the other hand, if they were to spin and end up on opposite sides, that's trans-isomerism. Now let's consider easy isomerism. This type of isomerism is a bit more complex, as it involves looking at the priority of the groups attached to the double bond or ring. It's like if the dancers were holding props and we had to decide who was leading based on the importance of the prop. If the higher priority groups are on the same side, we have a Z-isomer from the German zusammen, meaning together. If they are on opposite sides, we have an E-isomer from the German entgegen, meaning opposite. In the grand dance of molecules, these small changes in position can have significant effects on the properties and behavior of the compounds. It's like changing the music in the middle of a dance. The dancers must adapt to keep in step. Geometric isomerism shows us how even small changes in molecular structure can lead to significant differences in chemical behavior. So, next time you think about dancing, remember the intricate dance of atoms and molecules in geometric isomerism. In the world of chemistry, molecules are social. They interact, combine, and sometimes even break apart. And in this interaction, electrophiles, nucleophiles, and radicals play vital roles. Let's start with electrophiles. These are the attention seekers of the molecular world. They have a knack for electrons, always on the lookout for those carrying a negative charge. In essence, electrophiles are electron-poor entities that seek electrons to achieve stability. They're often positively charged or carry a positive polar site, making them irresistibly attractive to electron-rich molecules. Next, we have the nucleophiles. These are the givers in the dance of chemistry. They are electron-rich species that are attracted to electron-poor areas of other molecules. Nucleophiles, with their surplus of electrons, are always ready to donate a pair to an electrophile, leading to the formation of a new bond. They are the ones who initiate contact, reaching out to electrophiles in a bid to create something new. And then we have the radicals. These are the lone wolves of the molecular world, highly reactive due to their unpaired electrons. Radicals don't play by the usual rules of charge attraction. They can react with both electrophiles and nucleophiles, causing all sorts of chaos in chemical reactions. Their reactivity and versatility make them key players in a wide range of chemical processes, from combustion reactions to polymerization. So, these three classes of reagents, electrophiles, nucleophiles, and radicals, are the heart of chemical reactions. They drive the diversity of reactions we see in chemistry, from simple acid-base reactions to complex organic syntheses. Their interactions mirror the give and take, the push and pull that we see in social dynamics. Just like in a social gathering, the interactions between different types of molecules dictate the outcomes of chemical reactions. The world of isomerism is complex and fascinating, full of mirror images, rotations, and interactions. As we've journeyed through this topic, we've uncovered the principles of stereochemistry and explored the nuances of enantiomerism and diastereomerism. We've delved into meso-compounds and the intriguing task of assigning configurations, specifically R and S. We've also navigated the intricacies of geometric isomerism, understanding the differences between CIS, trans, Z, and E structures. Moreover, we've looked into the classes of reactions and reagents, including the roles of electrophiles, nucleophiles, and radicals. Each of these elements plays a crucial role in chemical reactions, and understanding them is key to grasping the behavior of molecules and the properties they exhibit. Isomerism is a fundamental concept in chemistry that provides a deeper understanding of the molecular world. So, stay tuned, explore more, and don't forget to subscribe for more insights into the captivating world of chemistry.